So, today I will demonstrate hydrogen spectra and determination of Rydberg constant. So, you know that the first this hydrogen spectra was uh, observed by the Balmer, John Balmer in 1988, and that spectra was fitted. That spectra was fitted with the empirical formula given by Balmer. So, that empirical formula was basically is like this: 1 by lambda equal to some constant 1 by m square minus 1 by n square, where m equal to 1 for Lyman series, m equal to 2 for Balmer series, m equal to 3 for I think Paschen series. So, n equal to 4, m equal to 4 for bracket. So, there are different series. So, but this m equal to 2, for that the whatever series we observed, that was in visible range. So, in spectrometer it was easy to see because of the visible range, because the wavelength of these spectral lines was in the visible range. So, that was observed first, and the wavelength of the spectral lines was measured, and from this empirical formula, if formula is like this, so exactly that wavelength was reproduced from this formula. In that case, one has to consider a constant. Later on in 1988, Rydberg generalized the Balmer equation for all transition of hydrogen atoms. Okay, so that means Lyman series, then Paschen series, bracket series, Kuhn series. Okay, so he generalized, and for that the same constant, whatever Balmer got the constant, so same constant was valid. So that's why this constant now it's called Rydberg constant. Okay, so today we'll find out, we'll determine this Rydberg constant. So this is the Balmer series for hydrogen source. So this for hydrogen atom, you know, this is the principal quantum number n, that is n equal to 1, n equal to 2, n equal to 3. So different energy levels are there. So the transition between n equal to 2 and the higher n equal to 3, n equal to 4, n equal to 5. Okay. So that transition gives different spectral lines in visible range. So that's what we tell the Balmer series, and the name was given of these spectral lines like H alpha, then H beta, H gamma, H delta. So it has also different colors. It's a red color, this green color, then blue color, light blue color. Okay, and their wavelength also, it's this. Okay, so if you measure this wavelength, and then Then if you consider the transition, so in case of Balmer series, say m equal to 2, m equal to 2, and then you vary n where n is greater than m, so n equal to 3, 4, 5, 6. Okay. So for different spectral lines, for different wavelength, you can, putting the different value of n, you can calculate this RH, Rydberg constant, and this Rydberg constant should come same for all spectral lines, and then one can take the average of this Rydberg constant, and that value is generally should come like this. Okay. So these are 10973731 decimal point 57 meter inverse. So sometimes we express in centimeter inverse also. So this is the basically background of this experiment. So one has to get hydrogen spectra, and from that spectra, using the spectrometer, one can measure the wavelength of the spectral lines. When we will measure the wavelength of the spectral lines, and this part for visible range, whatever you are seeing, that is sure this is the Balmer series, and m will be 2. Then you take n equal to 3, 4, 5, and then see this matching with the wavelength 1 by lambda. Actually 1 by lambda, that wavelength you are measuring. So using that wavelength, and this m is basically 2, and for n equal to 3, then this part is basically constant for the spectral lines. Okay. So this divide by this will give you RH. Similarly, for next spectral line, n equal to 4, okay, then again you can find out RH. So here I have showed this 4 spectral lines. So 4 RH value you can get, and more or less they should be same, but experimentally when we will measure, there may be some difference. So that's why we take average of those values, and finally we get the answer. Okay. So what is the experimental arrangement for this experiment? Experimental arrangement for this experiment, it's so to measure the wavelength, of a light. So PGM spectrometer is very popular. So in PGM spectrometer, so we put grating on the prism table, and then there is a collimator. In front of collimator there should be source of hydrogen light. So for other, if you want to measure the wavelength of sodium, so sodium source, or helium, if you want to measure the wavelength of helium light, so one can put helium light. Okay. So this kind of measurement we have done, I have demonstrated earlier. Okay, how to measure wavelength using the grating. So using that process you can measure the wavelength. Okay, this is the telescope, and then you can rotate the telescope to measure the angle. So that angle, if you can measure, then you can calculate the wavelength. Okay. So that's this is the d sin theta equal to n lambda. This is the formula for the grating. D is the grating element, and that value is given. Now if we can measure the theta using the spectrometer, so then from here I can write 1 by lambda equal to n by d sin theta. N is the, in this case, the order, first order, second order, third order. So if you take only one order, in one order different colors, in case of hydrogen or helium, you will get 3, 4, 5 spectral lines, and if you can measure the angle of those spectral lines, okay, that is basically spectral lines you will see because of the diffraction, and using this formula you can find out the 1 by lambda. Because here I have written 1 by lambda because in Rydberg constant there's 1 by lambda equal to RH, as I showed, 1 by lambda equal to RH, 1 by m square minus 1 by n square. So this n is different than that n, that is the order of the diffraction order, but here this n is principal quantum number. So from that measurement you can get the 1 by lambda. Using the grating you can get 1 by lambda. So for that you have to measure theta, okay, you have to measure theta. So that theta you can measure using the spectrometer. There is another alternative method for measuring this angle. So here I think in laboratory I will demonstrate this one, because many times I have used this spectrometer for different experiments. So this is another new method how to measure the angle, okay. So this method I will show you today in our laboratory. So basically here you can see that you have a light source, it's the hydrogen or helium, whatever, okay. So from there lights are coming, and here this one is a grating, this one is a grating. So light is coming, falling on the grating. So this you see this, when light falls on the grating, so it generates basically secondary wavelets, and that secondary wavelets will interfere and give the diffraction pattern, okay. So in this case, so diffraction pattern it can form in transmission side, also it can form in the reflection side, okay. So here whatever you are getting, so we are seeing the diffraction pattern in the reflection side. That means the light is coming and falling on the grating, and the diffraction pattern we are seeing on the same side, okay. If you see the other side, then it's the we tell this transmission. It's the other side, same side, then we tell the reflection, okay. So here basically we'll see when we'll see the diffraction pattern through the grating, then that pattern will observe on the same side of the source, and we have put a scale just behind the light source, and there we have indicator. So we'll see the image, we'll see the diffraction pattern there, means we'll see the spectral lines, and from the center, at which distance you are getting, the spectral lines of different colors. So that distance, that indicator basically will match with the spectral lines image of the source. So spectral lines whatever we will get, so that what will be the shape of that image. So that will be the shape of the light source. That's basically is the image of light source. So we'll see the image of the light source of different colors at different distance, okay, so that from the center what is the distance of the different spectral lines, so that we will find out, okay. So that means this distance we will find out. Now if you know this distance, screen to scale distance, this getting to scale distance, okay. So if it is capital D and this here I have written 2L, so basically we will not measure the distance from the center directly. What we will do, so we will get symmetrically first order of diffraction pattern on both sides, second order also on both sides. So in this case only we will be able to see the first order. Second order also one can see if you take this diffraction getting of higher number of lines. So at present in laboratory we will use a grating which is having the 600 lines per millimeter. So but we have seen that if you use the 1200 lines per millimeter, then we can see also second order. But presently in laboratory I will use the 600 lines of lines per millimeter. So we will see the first order. So on left side we will see the first order of different colors, and right side also we will see the first order of different color. So so this here I have drawn this the first order of red spectral lines. So we will measure basically distance between these two, and then half of it will give you this distance. So from the middle to the spectral lines, so we will basically measure 2L, then divide by 2 will give me this L, and this is D. So now sin theta will be this divided by this, right. So this is the perpendicular. So if this is theta, diffraction angle, so then sin theta will be this L divided by square root of L square plus D square, right. So if you can measure L and D value we keep fixed, okay. L will vary depending on the position of the spectral line. So basically we will take reading of this L, small l, then we will be able to calculate sin theta. So 1 by sin theta is square root of L square plus D square by L. So getting this data of L, we can get 1 by sin theta. If you get 1 by sin theta, D is supplied, so N is, in our case it will be 1, so you can find out 1 by lambda. So 1 by lambda for different colors we will find out. If you find out this, then you can calculate the Rydberg constant from this formula, okay. So that's the experiment we will demonstrate. So experimental data will record. So this type of table we will use. So getting element D. So as I told, this 600 lines per millimeter. So what is the separation between the lines? So that you can calculate. So that will be 1 by 600 in millimeter. So that will be the D. So that you should note down. It is, since it is supplied, distance between the screen and the grating, okay. So that capital D, whatever I showed you in figure, so that we should fix it, we will not disturb it, so that you should note down. So then now you see the spectral lines, okay, and for different colors you take reading, of spectral lines. It's the left side and this right side, take reading. Generally we take 2, 3, 4 readings and then find out the average of that one for a particular spectral line, okay. So that will be say this average is, say, from left side is reading is capital L and from right side is capital R. So small l, it will be difference between these two reading, left and right side reading, divide by 2, okay. So we'll note down this reading and then from there we'll find out L. So if you already I have told, so from this L you can calculate 1 by lambda, and when you know the 1 by lambda, so then you calculate RH, Rydberg constant, okay. 1 by lambda divide by 1 by 4 minus 1 by n square. So for n equal to 3 for a particular color, say red color, so you calculate Rydberg constant. For n equal to 4, next color, calculate Rydberg constant. So this way you calculate Rydberg constant 3 or 4 for 3, 4 spectral lines and then take the average of those RH and find out the final value of the Rydberg constant. So that's the experiment we will do. So let me show the experiment. I think let me also tell you about the error calculation. So our working formula is 1 by lambda equal to RH, 1 by 2 square, because m for Balmer series is 2, minus 1 by n square, okay. So this I can write RH into k constant, some constant, this is a constant for each n, okay. For each n is a constant value. So take the log on both sides, so minus ln lambda plus ln RH plus ln k. So k obviously is constant, we are not measuring anything, so it will not contribute in the error. So now differentiate it, del lambda by lambda equal to del RH by RH, okay. So what is del lambda by lambda? So 1 by lambda equal to 1 by d n by sine theta. So 1 by sine theta is this one, as I showed you, square root of L square plus d square by L, because you have to express the parameter in terms of parameter which we have measured to calculate the error, okay. So if you take log on both sides, so minus log lambda equal to minus log d plus half log this one L square plus d square minus log L, right. So from here you can find out del lambda by lambda equal to, you can see this d is supplied, so there is no error here. So error, so from this part half is there, so it's a log, okay. If you differentiate it, so 1 by this, 1 by this, and then this one will give you 2L del L plus 2D del D, okay, plus this part, because in case of we are calculating maximum probable error, so all we have to take all individual error you have to add, so that's why we are not taking minus sign, we are taking plus sign, so del L by L, okay. So from here basically this part, this half is there, so it's coming L del L plus D del D divided by L square plus D square plus this part del L by L, okay. Now L, you remember when you are measuring L, basically we are taking difference of two reading, capital L and capital R, left side reading and right side reading, divide by 2. Okay. So from here it's a del L is basically whatever del L here we will use, that is basically half del capital L plus del capital R. So this half is there. So this left side and right side we taking reading from the same scale. So del capital L will be equal to del capital R. So least count is same for that. So basically 2 into that least count divided by 2. So that is the del L is basically least count. So here whatever del L, so that is the least count of the scale we are using for the measuring the position of the spectral lines. And that capital D also, delta D here, so this also we have used meter scale. So here also its least count is 1 millimeter for del L. So there also we have used meter scale. So this least count is 1 millimeter. Okay. So del lambda by lambda from where here you are getting. So that is nothing but the del RH by RH. So error in RH you can delta del R or del R equal to whatever this value you got multiplied with this Rydberg constant RH. So that will give the delta RH. So error in the measurement, in the calculation of the Rydberg constant. Okay. So that's the error calculation. So next I will demonstrate the experiment in the laboratory.